Hi, I'm Emily Bamber. I'm currently a PhD candidate at the University of Texas at Austin in the Jackson School of Geosciences, and I'm here on my fieldwork collecting samples for cosmogenic radionuclide dating. I wanted to make a video to explain the sampling procedure to make the sampling process more accessible. So I'm currently here with my wonderful colleagues in the beautiful Dar Valley near the Lonar crater in Maharashtra, India. And we're standing here on the valley walls on a lovely terrace. I'm going to talk you through, with the help of my colleagues, the sampling procedures we're going through to collect samples here. We're asking the question, what erosion rates were present in the Dar Valley through its history, and also at what point did the valley form relative to impact crater formation of the Lonar crater. And we're going to be using cosmogenic radionuclide helium-3 exposure dating to answer those questions. But you can use it for a wide array of other questions as well. We're on a terrace and the river is about 10 to 15 meters below me down here. And we're also next to a waterfall. So there's been clear nick point migration from further downstream of here up to where the waterfall is today, and also incision from where the river was on this terrace to where it is today, much lower beneath us. And so we can take the difference between different points on the terraces to estimate erosion rates over time, and that will help us answer those science questions. This is one of our best exposures because it's really nicely fluvially eroded with these erosional lineations on the surface of the rock, and nice smooth surfaces which have been created by fluvial erosion, and also on other places you can see these like scoured surfaces which are smooth and sort of curved surfaces which were clearly created by fluvial erosion, which makes this makes us very confident that this sample was fluvially eroded and is part of this terrace and didn't form due to like rockfall or some other process. We assigned a confidence rating to each of our sites, which is a good thing, a good practice to do in case you then later get back to the lab and are like, why does this age not make sense? And so we gave us a confidence rating 5 out of 5 due to those fluvial markers, and also because we're fairly confident the topographic shielding has been consistent for this sample through time, thing one of my colleagues will talk about later. We're also confident it's not been covered by soil or vegetation, so the exposure age has not been affected by other factors attenuating cosmogenic rays, which again my colleagues will talk about later in the video. So I'm really excited to get samples from this outcrop and the other outcrops we have further down, and look at what story the ages will tell us of how this valley formed over time.
Hi everyone, my name is Gaia and I'm an assistant professor at MIT. Emily gave you a nice introduction as to why we're here in this valley, but now I'm going to give you a little bit of an explainer as to how cosmogenic helium-3 actually works and what we're actually measuring specifically for this site. And so, first of all, before you start sampling, you want to have a little bit of an idea as to what is the history of your location and how it was formed. And so here in the Lonar crater, we know that these basalts were originally formed about 65 million years ago, and so we have the Deccan traps that were nicely erupted around that time and formed this nice, basically flat plateau. And so that's when these rocks originally formed. And so what happens when rocks form is that now, for the first time in their history since crystallization, they are exposed to the sky. And the sky is filled with these invisible rays, which are cosmic rays. So you get all of these rays coming straight from outer space that touch and basically hit the surface and can even go through the surface. And what these cosmic rays do is that they actually interact with the minerals that are in the basalt. So this is a process that's called spallation. And so when a cosmic ray hits, it basically causes helium-3 to be produced and to be stored in the lattices of minerals. And the minerals here would be olivine and pyroxene, and that's unique to basalts. And so we basically get helium-3 accumulating over time, and because it's a stable isotope, it doesn't decay. So the more time that goes by, the more helium-3 remains in the lattice. And so what that means is that you can basically get a measure as to how long a surface was exposed to the sky just by measuring the amount of helium-3 in a rock. And so luckily, because it doesn't decay, if you were to draw a nice plot of the number of helium-3 as a function of time, you basically get this nice linear function that looks like this. And so if you measure a certain n, a certain value of helium-3 for your sample that you picked up here, you can find out when exactly that was formed in time. All right, so this is really great if you want to date when this basalt was formed, when it was erupted. But this is something that has actually already been done. And as you saw from Emily before, what she was talking about, we're not really interested in the eruption or the formation of this plateau. We're interested in erosion rates. So how can we use this idea to actually calculate erosion rates in rock? And so the basic idea is very similar, but instead of measuring the exposure of a surface when it was erupted, we're basically measuring the exposure as to when it was cut into, when it was incised. So here we have a valley going back here in like a 3D perspective, and then you can see here in red there's some river terraces that have also been incised. And so what we want to do is find out when this rock here was exposed in time, and then we can also basically trace back through the terrace to find out the retreat rates of a waterfall, for example, that is flowing here into this river here. And so the idea is exactly the same. The only thing you have to be careful about is that if you go back here, of course, if you were to sample a terrace that is somewhere in the top 2 meters or so, then you have to be very careful because you are probably measuring cosmogenic helium-3 when the original basalt was formed. So when you are measuring helium-3 from terraces, you want to make sure that you're far away from that original lava flow surface. And there can also be multiple lava flows. And so whenever you do measure terraces, just make sure that you're avoiding those top 2 meters. And that is if you're looking for erosion rates. Of course, if you're interested in when the basalt was erupted, then that is where you have to focus your helium-3 sampling. And so I talked about this linear production rate, number of helium-3 as a function of time, and said that it was quite simple, but it's not actually that simple, of course, nothing ever is. And so we do have to know what this production rate is. We're measuring n, and we want to find t, but we need to know what the slope of this line is. And that is something that's called the production rate, and it can vary geographically for different locations. So you basically have to go back into literature and find out what the production rate closest to your sampling site is. And then there's a bunch of other factors that still affect how much cosmogenic helium-3 will reach your sample. And we're going to talk a bit about some of the main ones that we need to account for in the field, but there's many that you can account for out of the field. So for example, the altitude of where you are, this is something that you can look up or with your GPS later on. And of course, if you're in Mount Everest compared to its sea level, there's a very big difference in how much atmosphere is above you, and that's what affects how much cosmic rays can actually interact with the surface. And so altitude is one thing that you'll need to put into your production rate, and there's calculators online that can help you do that. And then things like the latitude as well. So if you're at higher latitudes or closer to the equator, this also affects how much atmosphere is between you and the source of the cosmic rays, which is outer space. And so those are a few of the things that will determine this relationship here. And then we're going to be talking a little bit about how we can account for other factors that come into it as well.
Hi, I'm Sharanya Achandran, PhD candidate from the Department of Geology, University of Kerala. This Lonar crater, it forms a part of the Lonar Wildlife Sanctuary. So before taking samples from regions like this, we have to make sure that we have the proper permission from the authorities. So for that, we have permission from different government authorities like the Indian Forest Service, Archaeological Survey of India, and the local governing bodies around this area, and we are forever grateful for them for giving permission. Before taking samples, we have to note that in every geological fieldwork and in every sampling, we have to give proper sample numbers to the samples. For this particular sample, we are naming it like Lonar. This is a part of the terrace here, and the sample number. Before taking samples, we can take a good number of photographs in different scales and from different angles, so that we'll get a good idea of from where we took the samples Then we can proceed to take the samples. For sampling, we can use different methods, like we can use the conventional sledgehammer and geological hammer, and if it is difficult to get the sample, then we can use portable grinders also. In this case, we are going to use a sledgehammer and geological hammer. So by taking samples also, we have to be very careful. We should take essential precautionary measures like wearing goggles. After breaking it from the exposure, we got a good sample from this exposure, and there are several factors which affects the cosmogenic nuclei dating, and one of it is the depth from the surface. And so whenever we are getting a sample from the exposure, we should measure the thickness of that sample, because as the thickness of the sample increases further downwards, the production of cosmogenic nuclei will be decreasing, and it should not be much thicker, but it should have a good amount for the analysis purposes, and it should come like around 1 kilogram. So let's take an average measurement of this particular sample using a ruler. So you can measure it like this. So it comes like around 5 centimeter. Besides measuring the thickness of the sample, we can also measure the horizontal distance between different sampling spots. Here we are taking the motion of the river further backwards, so how it erodes the valley over the thousands of years. So we need to get the difference between different sample locations. For that, we can use conventional methods like using a measuring tape, or we can use high precision instruments like RTK GPS. With that, we can take the difference between from location A to location B and from location B to location C. So that would give a relative difference between these terraces that are exposed along the course of the backward motion of this particular stream.
Hi, I'm Devika Patnakumar, a project fellow from University of Kerala. So I'll be talking about how to take field notes. The first thing you need to have is a field notebook, just like this, and you have to write the date and you have to write the sample name, and then you have to take the GPS location from where you're going to take the sample. So it doesn't matter whether you don't have to have a sophisticated RTK GPS. You can use simple handheld GPS for taking the measurements. And after that, you can take the elevation and the waypoint. So that's the first thing you have to do. Okay, the next thing that you have to mention in your field note is that what are the significant erosional features that you see in the exposure or from the rock from where you're taking the samples. So here we are mostly interested about the fluvial erosional features, and like Emily said before, you can see the fluvially eroded smoothened exposure, and you can see the scar marks on this side. So we are interested for that.
So here you can see this piece of exposure has lots of fluvial features, fluvial erosion features, but we are not interested in taking samples from this location, is because this exposure has good amount of soil and it's highly vegetated. So that means why we didn't choose is because the soil and vegetation can affect the attenuation rate of the cosmic rays. So even though if we're confident that we're on the terrace or the valley wall, but there are certain locations we're not interested in sampling, because you can see this exposure here is highly appreciated, and we suspect that it is on the top of the lava flow, and we're not interested in sampling because it might give the age of the lava flow and not the age of the fluvial erosion that we're looking for.
Hi, I'm Prakhar Sana, a postdoc from MIT. So I'll talk to you a little about an important correction that must be included while we measure exposure ages using cosmogenic dating. We have a parameter called topographic shielding, which determines how much of the sky is open to the sample. And so if the sample was collected from a flat surface, which is open to the entire hemisphere of the sky, you have all the cosmic radiation reaching it. But that's not usually the case. You have topography around it, which blocks the cosmic radiation that ideally would have reached the sample. So we have to consider that factor as we are using this technique to get exposure ages. To calculate topographic shielding, we use an instrument called sighting compass clinometer, which has a compass on one end and a clinometer at on the other side. So what I would do is pick up a topographic inflection point, usually a high or a low in the topographic profile around the sample, and find out its direction relative to the location of the sample. To use this device, I have one eye directly looking at the topographic profile, and the other eye looks at the direction measurement, which is azimuth, a compass reading given by the device. And to measure the inclination of the profile, you flip the instrument and look at the same topographic point and try and match the crosshair in the instrument to the top or the bottom of the profile that you've been looking at, and then read out the inclination measurement. So you carry this out for all of the highs and lows 360 degree around the sampling location, and that gives you a 360 degree topographic profile. And once you have that, there is a measure of what percentage of sky is open to open to the sample to receive the cosmic radiation.
Hey, myself Karan. I'm from master student from Savitribai Phule University, Pune. I'm just showing to you how to take a reading of topographic shielding. This is the this is device we are using for the topographic shielding measurements. So it's time.
Roughly 10 measurements of azimuth and inclination are sufficient to get a good estimate of a 360 degree topographic profile around the sample. But you may take as many as you need.
So thank you for watching. We really hope this was helpful for you, and we all wish you good luck on your next field adventure.
Something called I forget. Oh, the sound.
Did I forget something?
No. Like and subscribe.